So it's Ben Holcomb here, Associate Professor in Mechanical and Mechatronic Engineering at UTS, back in the Vibration Lab, second part of a two-part video on relative accelerometer calibration. Previously looked at different types of accelerometers, the accelerometer calibrator, the handheld calibrator, explained the nature of the setup here, talked about transducer data sheets and the way that transducers vary. Now I'm going to do some relative calibration in software of these devices. What we've set up here to give some more detail on this is an industry standard, off-the-shelf, commercially off-the-shelf, integrated electronic piezoelectric transducer here directly onto the calibrator, stud mounted. So this is stud mounted onto here. The device on top is similarly a piezoelectric transducer, but in this case the signal conditioning, rather than being provided by integrated electronics piezoelectric, is provided by a fiber optic based solution, a bespoke solution by one of our industry partners at Vibration Lab in UTS Tech Lab. And the important part of this process is that we need to calibrate this optically conditioned transducer to give flat frequency response, and in this case the optoelectronics are not necessarily as manufactured giving that kind of a flat frequency response that we need for a transducer. So step one is going to be to have a look at the response for a single frequency, and then we'll do broadband calibration subsequently. So in the software, which is Siemens SimCenter Test Lab spectral testing, I can set up my three inputs. So I've got the laser vibrometer on the first channel. This is producing a voltage. We're AC coupled. I have defined the measured quantity as velocity. It has a nominal sensitivity of 1000 millivolts per meter per second. We've configured the device to give 10 millimeters per second per volt. The actual sensitivity is the same. We trust the vibrometer, that's kind of our reference, but we're also using the calibrator to provide a reference. This is our piece, this is DJB Instruments AF/100/10 transducer. It's ICP powered, IEPE powered. It's got a nominal sensitivity of 100 millivolts per G, an actual sensitivity of 99.43 millivolts per G as per the box that it comes in. With the optical transducer, we are similarly AC coupled. We're measuring voltage, its acceleration. We've given it a nominal sensitivity of 1000 millivolts per meter per second, essentially 1 volt per meter per second. We don't know the sensitivity of this transducer yet. The actual sensitivity similarly would begin life as being 1000 millivolts per meter per second. And so if we do that, then we can have a look at, in the oscilloscope sheet, the comparison between these transducers in terms of the vibration that performs. So if I turn on the accelerometer calibrator here, you can see some sinusoidal frequencies. We're measuring over a 4-second duration. I've got the velocity here. Okay, I've got the acceleration for the off-the-shelf transducer here and the acceleration off the optical transducer here. You can see that this value is different to here. We're displaying engineering units, so we need to update our actual sensitivity to give us the same readings on these two. We've got 14.55 peak for the IEP accelerometer and 6 times 10 to the minus 3 meters per second squared for the optical transducer. So one of those is overreading. This should be 14. They should both be giving us 14.14 meters per second squared, which is the peak vibration at this frequency that this calibrator is producing for us. If we go to a table that I've prepared, this is our original actual sensitivity for the IEP transducer. It's 99.43 millivolts per G. We had that from the transducer box or the data sheet. The optical transducer, we didn't know what the actual sensitivity is. That's what we're trying to find out. So we've just said 1000 millivolts per meter per second squared, or 1 volt per meter per second squared. That's going to be significantly incorrect. Our actual level is 14.14. That's what we should be seeing on the measurement system. From those two time traces, you'll recall we had 14.57 meters per second squared for the IEP transducer, 0.0060 meters per second squared from the optical transducer. We need a correction factor for these two sensitivities that we can specify in place of these ones, such that these two values are equal to that, our actual vibration level. To do that, we divide the actual measured value by the amount of vibration there is for both transducers. We get correction factors of 1.0304 for the IEP transducer and 0.000424 for the optical transducer. Remember, I told you that this was very wrong. It was way too high. Okay? Then we take these correction factors and we multiply those by the original sensitivities to get a new sensitivity. And if you're unsure about how this is all working, remember that this one will be dimensionless, okay, and therefore the units don't change. So in this case we're going to have 0.0424 millivolts per meter per second squared that we need to enter instead in our acquisition system. Okay, so 0.000424 times 1,000 gives us 0.424. Let's go back to the channel setup, change those values in the software. So there we had 99.43 and we changed this one to 102.44. This one we had 1,000 millivolts per meter per second squared. We changed this to 0.0424. We accept that value. We go back to the scope sheet. We turn on the calibrator once more to produce our reference vibration level. And we have a look at these two measurements, and they should be, once it builds up fully, pretty close to or exactly 14.14. They fluctuate a little bit because there's noise in the environment, the table's moving, they differ a little bit from one another, but they're now pretty close and pretty closely calibrated. That's a relative calibration process. That's the end of this video.